I'm Eric Udren. I'm with Quanta Technology, and I'm based in Pittsburgh. If you're looking at your printed program, surprise, this isn't the topic you thought you were getting. That was a misprint at the end. My mentor, Dr. Damir Novosel, and I thought we nailed fault location 20 years ago, and we're going to talk about protection, which seems to be something of a third rail in some synchrophasor applications. But in fact, it's one of the simpler things you can do, and that is my message to you for, this afternoon. I look out at this room of industry experts, and I contemplate that this is a subset, a small subset of the group of people who now have employment, and also quite a lot of excitement because of the creation of Jim and Arun and all of their collaborators. It's quite exciting to be here as a part of that. We all, we met quite a number of decades ago. It was in the early 1970s, before synchrophasors had been invented, that Jim and Arun worked in New York for AEP. We've heard about that. I worked 10 miles across the river in Newark for George Rockefeller, the inventor of digital relaying, and all of us were pioneers in the field of digital fault protection. In fact, the work that was done at AEP really spawned, as we've heard, the creation of PMU concepts. But at our hearts, we were all relay engineers, and we still are. So I look at what we have here and say, what can we do in the fault protection area? And it's not hard. Now back in 2010, Damir and I gave a presentation at the PacWorld conference, which was in Dublin, Ireland, and we gave what we considered kind of a roadmap for deployment of wide area monitoring, protection, and control. Not just the monitoring, but the protection and control. Visualization is valuable, and it's important, and it's where we start. But to get to control functions, as we've heard today, there's a lot of work that folks have to do with getting better models, testing out algorithms, seeing in a model fashion how they're going to work, and eventually someone's going to actually put it on a live system and observe how it works, and we have some distance to travel before we close the loop. We know this is going to happen. We're going to have protection and control. We all believe in it, but it takes a lot of time and investment. Now, when you talk about protective relaying, using synchrophasors over a wide area, you start worrying about, okay, who's going to take this risk? We have risk aversion when we start to trip circuit breakers, and if we're doing it over a wide area, we're worried about creating a black box. And that's true for any of these control functions. So, while we worry about this, and don't do it, PMU infrastructure is being deployed. We're getting a lot of it. We know that the ultimate business case is not just visualization and situational awareness, it is control, not leaving everything up to the operator who can only react so fast, but control and protection. We're all here doing the work we're doing because we believe that if we build this PMU infrastructure, the applications will come. We have faith in that. And we think they're going to work because the fundamental phasor measurement principle is as robust as an airplane wing, is the way I like to describe it. You know exactly what you have to do to make it work, and it always works the way you expect it to. We know what we're going to get. There is a closed loop function that's really very easy to conceive and to do. And that is wide area, actually it could be primary, I use the word backup, but fault protection using current differential relay, Kirchhoff's law. This is another principle that's simple at its core. It's another airplane wing, if you will. I'm not claiming that this is a new idea. It's been discussed for decades as a fundamental concept. The most recent written record of this is in this IEEE PSRC report. And in that report they said, yeah, you can do this. And in fact, it's nice because now our current values have time tags on them, so we don't depend on measuring channel delays the way we do in normal line protection relays that do current differential relaying. So yeah, for sure you can do this. That's as far as the report goes. But that doesn't quite get us to a working application. We can say, we know what we need to do to make a practical application, and we know everything we need today. There's just a lot of details, like making a real airplane out of those robust wings. A few of the basic ideas here. I don't know if everyone here has protective relaying familiarity enough to know about current differential measurements where you're looking at the currents going in and out, but it is just Kirchhoff's law. Because the measurements are not available at the same place and the same time, we need to know the timing. We either measure the delay, or we have the time tags in the case of synchrophasors, which is beautiful and simplifying. We can take the thing we already do and have been doing for many decades on transmission lines, buses, transformers, and we can do it across the whole power system, nesting our zones of protection using these phasor measurements of current. There'll be other things we can do with voltage that I'll mention briefly. There are beautiful advantages to doing this. It is, in particular, compared to today's distance relay backup-based methods, we get predictable measurement times and very precise, surgically precise knowledge of exactly where the problem is, and therefore exactly what to do, where to trip. We can do the right thing. Our zone 2 and zone 3 relays don't always operate so selectively. And we get predictable measurement times, so it's actually possible to talk about reducing backup clearing times, a great benefit to system stability improvement. When you actually look at how to do this, today is not a good time to start laying out detailed strategies for how this would get done. But there are a variety of nested sequence strategies for how we could use this differential current measurement to detect where a fault is, what's going on, and how to disconnect it. We can even duplicate the primary protection. It'll be a little slower than the current differential relays we have today, and issue kind of an additional set of trips to the breakers that should clear a fault. We can do breaker failure detection by its effect as well as what's going on at the breaker, and do the backup tripping that would be done for that. We know what's going on with the data that we have. Remote backup is tripping adjacent zones when we have no measurements from or cannot get clearing to occur on the primary zone where the fault is located. I would not advocate in this work that we get rid of all the distance and overcurrent relays that we have out there, but we fundamentally change their settings so they're slower, farther reaching, and they're aimed at safety net protection and not at the job of backup clearing of faults when the primary systems don't work. A few more ideas regarding how we might do a system like this. We've got to have some sort of collection of the data. That can be distributed, so you can have controllers at various places with program logic that would be receiving synchrophasors. It might be tied to or part of PDCs, and they would compare data in relevant ways, or you can centralize the whole thing and have a big set of redundant controllers, the way we do with many of our remedial action schemes or SIPs today. So we can have centralized or distributed processing. For the time frames we're talking about, any of the phasor measurement methods that we have out of the standards, the 2005, the 2011 standards, all of them would work for this. We have enough time for the values to stabilize and work fine. Communication latencies that you see here, even if we're using an Ethernet wide area network, these time requirements are not at all challenging. In fact, they're already a lot faster than what we need to do this. We need a downward control path. We do have that. And we can achieve in the future, at the rate things are going, wide area protection response as little as 100 or 120 milliseconds. In fact, we probably can't set it that fast because we still have to wait for circuit breakers to do their job. Why do we want to try something that's quite different from what we're familiar with and that we feel comfortable with? Well, the schemes that we have today using zone 2 and zone 3 relays have massive coordination challenges. I can tell you that a lot of my colleagues and I actually have a lot of work that we do helping utilities review their coordination. It's a giant job, a huge project to go through and see if these relays are set correctly. And you have to do it all the time because the systems are evolving, fault current contributions are changing, and you can lose coordination. If you don't have really good physical data on exactly what the transmission line or the other apparatus looks like, what impedances are and so forth, you're going to get errors from that. And then you find miscoordinations and you can't even fix them. You just have to make a bad choice and do something. So these are all problems with these existing methods. And there are more problems. In recent years, we've had loadability limits that came to us after the 2003 blackout. We have new energy sources that I've pictured here, which have low fault current contributions, in some cases making it harder for us to figure out where the fault is or to set these distance relays properly. And maybe something that's observable and not technical is that all the folks who knew how to deal with these problems are retiring. We're losing this ability. To do a wide area protection scheme, such as I'm describing, requires a whole lot of communications that we are in the process of building. And the communications are going to be the most unreliable part of this system. And I've thrown some numbers up here just for consideration. So we have to look at redundancy or methods that we're going to assure reliable communications. I should point out that because we have layered backup possibilities with this methodology, it has, even if we lose some of our communication paths at times, something that's going to clear a fault. But for a really critical backup application, we're going to go to a redundant system. We show here an architecture for a WAMPAX that would do protection or even the control functions that some of our speakers have been talking about today, in which we have no single point of failure because we have redundant communications as well as PMUs and controllers that would do the fault protection. In the communications arena, it's interesting to consider that there's actually capabilities available that some of us are just learning about. They're outside suppliers. When we talk about covering the continent with reliable communications, some of us have heard about Chuck Newton, our industry research expert, and I were talking about earlier. We've seen the Harris installation of communications system for the FAA air traffic control system. This is an N-redundant system. They have lots of redundant paths. They're fully isolated by wave division multiplexing. And they have a reliable mission-critical system that's proven. And this is actually a model for reliable wide-area data communications, the type we need to do these protection and control functions. And in fact, WEC has begun work with Harris on creation of a system to cover the whole Western interconnection. No one utility has all this infrastructure. We need cybersecurity, and we have a new protocol for that. Vahid Madani and his supplier partners, including GE, Mark, and Alstom, we've heard from both of them today, have been implementing IEC 61850-90-5, which will send messages over a wide area. It adheres to 61850 principles, but I won't connect it with that. You can use it all by itself. And it includes extremely or fully rigorous cybersecurity measures so that you can authenticate and encrypt all of the data and not be vulnerable to any sort of a cyber attack, even if you're worried about that. We also know how to do time synchronization over the network. There are a few application issues with what I'm talking about, and it would be a longer discussion to go through some of those, but we know how to deal with these. So CT saturation, we already have figured that one out for the line differential relays that we have, and we can apply those methods in a wide area as well. If you have some sort of a fax device in the zone somewhere, here's something that will take a little bit of charge out of one phase and dump it in another one to achieve some operating benefit. So we need to know something about its state and or observe its signature in order to know how to deal with it. I would claim that we'll be able to deal with that with no problem. Same thing with shunt reactors and capacitors that are also fault-like leaks in and out of the zone that we're protecting. Protection engineers who are looking at backup protection are always worried about that so-called dead battery station for which we want our zone 3 relays to look without analyzing the whole problem. There will be some compromises in the scheme when we do that, but it knows when it's lost its data from a dead station, and there are things that we can do. And so, to wrap up this presentation of an idea that could get me thrown out by some of my relaying buddies, the WAMPAX infrastructure that we're talking about building can handle and can do this current comparison backup relaying. As opposed to all the model refinement work that we've talked about today, which is important for many of the control functions, we don't need it here. And in fact, it overcomes the problems that we face with bad models in terms of protective relaying. And we could demonstrate this now with many utilities deploying large numbers of PMUs. We could run no-risk demonstrations in which we can see when or if it's going to trip and learn that maybe this is a good thing to do. And the PMUs are going to be there. We heard about that today, and there's my map of where the PMUs are going to be in the future. Thank you.